Next up is Harsha VISWANATH from Microsoft, who will talk about Azure Percent and tinyML. Take it away, Harsha.
Thank you, Adam. Hi, everybody. My name is Harsha VISWANATH. I'm a principal AI technology leader here at Microsoft. It's my pleasure to talk about Azure Precept. We just released that about 4 weeks ago. And also, I'll talk about neural networks that are applicable to small device footprints as well. So what we'll talk about are basically a couple of topics. Like I said, I'll give you an introduction to what Azure Percent is with respect to vision and ear products. And also, like I said, we'll talk about some of the neural networks that are applicable, what we are doing with Microsoft Research, and the way we are targeting that to Azure devices. Particularly this neural network called RNN pool, which is showing a lot of promise. So what is Azure Percent? So like I said, we introduced this about 4 weeks ago, 3 to 4 weeks ago at Ignite, Microsoft Ignite, and it has been received with great enthusiasm in the industry and users as well. So we are very excited. So what it is basically we're trying to democratize AI to the edge. You can think of it that way, right? So basically, you have all these IoT devices, like videos, audio devices, and so forth. So we want to make it easy for users to take that and kind of plug and play to Azure and get that working in, say, 10 minutes, right? And we want to wow everybody with that. So that's the experience we want to have. So in order to do that, there's a lot of work behind that, right? So some of the things we are doing there are, for example, we have 3 pillars, basically, what we refer to as pillars. The first one is we enable hardware reference designs with respect to the design kits and dev kits. So once that's enabled, so we build an end-to-end solution around the dev kit. So that is basically, in terms of Azure deploying machine learning workloads in a very secure way. Security is super important. We are looking at retraining these models, from the edge, sending the data back, and also the models have to be at rest. They have to be secure, and then once they're sent out in transit, they have to be secure as well. So we have encryption, decryption, all that stuff. So this is pretty cool in terms of all the security aspects. And the other aspect is basically the end-to-end ecosystem. So what we are trying to do is, initially we're trying to enable first-party devices. And as we go forward, we want to take that and scale it to third-party devices. And so what it's like, you can think of it as what we did with Windows back, 25, 30 years ago. We started building reference systems, and then once we had reference systems, we scaled it out to third-party vendors, and it became extremely successful. So our plan is to, in the next 4 years, I think 2025, our general manager, he has this great vision of having 1 billion devices of these guys at the edge. So how does the Azure Precept look like? So we have basically 3 components here. So this is one of the devices, by the way, in the slew of devices that we're going to release. So the first, the one in the middle you see there is the actual the control unit, which basically houses the ARM CPU, which is an NXP processor inside. It has the connectivity, which has storage. Encryption, decryption units, or I should say, both encryption and decryption. And then we have on the right side, we have the Azure Percept Vision module, which houses the, right now it's the Myriad X module. And then that does the heavy lifting. And then on the left, you have the Azure Percent device, which does basically the acceleration for keyword recognition and command word recognition. So this is, it works in tandem, all three together. And then they're easily installable in enterprise or user locations. So now let's kind of switch gears, right? So since this is a tinyML conference, I thought it would be nice to kind of give you a flavor for how we are looking at these devices and how we are getting neural networks that are appropriate for these devices, so that we can get, in the end, it's all about user experience, right? The more we can pack into these devices, these neural networks, we can have a cascade of these, and then hence, you have a better user experience. And also, of course, we have to maintain the accuracy. That's a given. So having said that, let's go here. So what the existing, what in the industry today, what has been done is you basically do model compression, right? You do decrease the size by pruning the network, do sparsification, then you decrease the compute as well by doing separable, depth-wise separable convolutions. There are all kinds of networks being introduced, mobile nets, and all and so forth. And what we are proposing is this novel scheme. One of the proposals, right, or one of the algorithms we have implemented on these devices is basically we take a big image, a full-size image, and then we do patch processing all across, right? And then on those patches, let's say you have a 16 by 16. In this case, I think it was a 4 by 4, where we you can think of it as subsample going down to one pixel, right, from a 4 by 4. And then you run it across in a raster scan way. And then you also do it column-wise as well, right? And then you get, a 3 by 3 in this case, right? So you can think of it as going from, say, one of the initial layers, and then going all the way down to a further along in your processing, right? Like 3 or 4 layers down, and avoiding all that, and still maintaining the feature sets or feature space, right? So that's the beauty of this. Internally, we're doing this processing. The magic is with the LST, recurrent neural networks, that is doing all the feature extraction. All right. So this is an example of what we have done. Taken this network and run it through, what do you call? I can't see this thing here. 1 second. When I'm speaking. Okay, that's better. So we run this on a product, on a shelf with products. And like you see here, we have great detections here. Very few false positives, or none at all, actually. Very few, if at all. And then there are very few false negatives as well. So we get mean average precision 0.82, and then compared to YOLO v3 0.73, and you look at the compute, right? It's drastically reduced, and then the RAM size is drastically reduced too, right? And then if you compare it to actually YOLO, tiny YOLO, which is maybe a more appropriate comparison, the max there required are about 5 gigaflops, and then RAM size is lower as well, but you still see the incredible gain that we have with this, right? It's the beauty of this. So what we have here is oops, why isn't this showing up? Yeah, there you go. So we have this from, let's say, take this network here, right? 224 by 224, but go to the first convolutional layer, 112 by 112, and then you go through this RNN pool. It kind of resizes it to 28 by 28, but it does all the feature, it catches all the features and puts it in the subsample space, right? So that's the beauty of it. So if you want to check it out, it's in github.com, Microsoft, the link that is given below. Feel free to go. There is a complete source code and documentation and everything. So feel free to go and check it out and even put it on your devices, right? Thank you. That's what I have.
Thank you very much, Harsha. Actually, I am very curious about this RNN pool topic. Is that, I guess, I'm assuming because you mentioned LSTM earlier, the RNN really stands for recursive. Why I'm curious is normally in image processing, the problem is not because the receptor field could be big, could be small. Normally, you're kind of just running a convolution to try to kind of look at a region, but because translation invariant, we have to sweep across. Are you trying to kind of combine the context as you raster across of where you're at to combine it with essentially with a one-by-one convolution in one shot?
So you can think of it, Adam, you can think of it as, as a subsampler, right? Going, let's say you have a 4x4, and then you're subsampling it to 1 pixel, right?
Yeah.
But you're not going through all the different other layers. Maybe 4x4 is not a good example. Let's say you have a 16x16 and you're going to 1x1, right? Yeah. And you're avoiding all these other layers, right? But the way you're extracting that information is through doing the recurrent neural network inside that patch. You can think of it that
you have several layers inside. So the recurrencies is still within that window.
The patch, yes.
You're looking at. But there's nothing carried over from one position to the next.
No, it's within that patch itself.
Interesting. Okay.
Yeah.
And so how do you deal then with different, vastly different sizes of objects?
Vastly different sizes of objects. Well, it's invariant to that, right? Because you're doing it locally. You're trying to do it on a feature by feature basis. Let's say you have edges and things like that. You're trying to extract the gross, features as you go down, right? You're not trying to do it on an object by object basis.
Okay, so you're doing basically have a whole chain of these getting to smaller and smaller receptive fields.
Yeah. Yeah. You're just basically trying to preserve the entropy, basically.
Okay, that's very, very interesting approach. And then another question about the first topic, the Azure Percent. So you were saying that today it's what you call first party IP. First party hardware. When do you expect to support third party hardware?
That's a great question. So I can't give you the timelines, but we have, it's going to be maybe not this year, but next year or so. I can't tell you the timelines. Sorry.
Okay, but that's at least we know there is a plan for that.
It's coming soon, yeah. But in the meanwhile, you can expect different footprint devices. Like for example, today it's a pluggable device, right? In the future, near future, you can also expect tiny devices where you can peel and stick somewhere, right? With 4 AA batteries, for example, and then you could have another, what we call a bigger aggregate device, where you could have like a T4 kind of footprint, right? Where you do multiple streams of processing. So we are looking at a slew of devices.
Okay.
Yeah.
Thank you very much.
Thank you. Thank you.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group, Edge Impulse, EMSA, Gray Matter Labs, Greenwaves, HiMax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.